Well, in fact, as usual, I'm going to indemnify myself by starting 2 recordings, and hopefully at least one of them will actually arrive on schedule. I mean, I'll actually get a reasonable recording out of all this. So it's the 23rd of July, as you probably know, and this is what I'm going to do. So I'm going to place the coursework, the next coursework, on Saturday, in other words, tomorrow, probably in the evening. And I want you to submit that in a week's time. Okay, so the coursework is going to be based purely on what we're going to do today. So you shouldn't have any problems in doing it. It's a bit of a hassle having to spend time to do these things, and in a sense, my preference would be to have a live interactive question session, and I could ask you questions, and we could get everything sort of nailed very, very quickly indeed. But to summarise the issues about coursework, I gave you a coursework in the very last week of last term before the exam week, and I've actually set you 2 fairly short courseworks in the last fortnight, and I'm working up to giving you a third coursework, and I want you to submit that, as I said, in about a week's time. You can ask me questions for the entire week if you need to. I mean, it's not being particularly brave to ask me questions. I'll do my best to answer your questions, and this is part of what I'm here to do. I'm here to help you. Okay, so this week, and I've no idea whether you've actually studied this on your own or elsewhere. We're going to consider mutual exclusion and reflect on it, and to come to understand its significance in mission critical systems and also in everyday life, because the need for mutual exclusion, and I'm going to define what I mean by mutual exclusion in a short while, it is absolutely important, and we encounter it in almost everything we do, in every place that we are, in every circumstance. And I want you to realise that and take it seriously. And in addition, we're going to examine mechanisms or methods for implementing what I call the principle of mutual exclusion. And just to anticipate a little bit, mutual exclusion simply says you must, in certain circumstances, ensure that 2 actions aren't taking place at the same time using the same resource. And the resource I'm referring to is very, 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 very general indeed, and it covers an enormous, almost an infinite number of different objects around us and in the universe. So hopefully you can see you can see this overview, and we're going to note that attempts have been made to gain mutual exclusion using pure software alone, and I think it was one Dutchman, a very famous computer scientist called Dijkstra, who managed to eventually to give a convincing proof that 2 programs would enable those 2 programs to respect mutual exclusion. I mean, it's not trivial to do it in software, but mutual exclusion generally relies on hardware to achieve compliance and like arbitration. So we're going to have a brief look at that. Gaining mutual exclusion in Java is going to be mentioned only briefly because Java does actually have a keyword called synchronized, which enables us to respect the iron law that the principle of mutual exclusion actually states. So, and the second theme of today, so there's a fair amount to discuss in the first part, but the second main theme that I want to address is simply that of basic Boolean algebra. I mean, for all I know, you've done a lot already, or if you've been doing anything like computer studies or information technology, you probably will have come across and understand Boolean algebra to an extent. But I want to remind you of its importance and its relevance to computer science, and also its applicability in designing digital systems, design for digital systems, its relevance to programming, and indeed its relevance to logic-based systems. In other words, programs that are purely logic-based. So I don't know whether that idea is familiar to you. But there is what is now quite an old programming language called Prolog. So it's just Prolog, and it's called programming, which is short for programming and logic. And using Prolog, it is absolutely brilliant for a range of applications, ranging from what are called, or what used to be called, expert systems on the one hand, and to very practical applications like a route finder of, I mean, it could the application area could be all the roads in Great Britain, and all you really want the program to do is to return the route starting from where you are to your destination. And the program itself is great because it only takes a few lines of programming and logic code to do that. So it's brilliant. It's absolutely brilliant. And I'll talk a little bit about programming and logic because it is an important area. And if you were interested in computer science, if you're interested or still interested in computer science, you still want to do a little bit more, logic plays an important role in the languages for databases and database interrogation. You can formulate a query in logic and interrogate a database in very complex ways, and the database will actually return the answer to your logic query. And we're going to, as part of the Boolean algebra, we're going to have a look at De Morgan's law. So I don't know whether either of you heard of De Morgan, and I'm going to talk about that because you can. Okay, Mustafa, great. You can, amongst other things, reduce the complexity of an arbitrary logic expression. I mean, maybe it's very, very complex, and by repeatedly using De Morgan's law, you can actually simplify the expression, and that is very relevant to reducing the costs of digital design. In other words, if I'm making a chip and I can actually reduce the number of logic gates needed to implement the design, then that's wonderful. But it's also quite useful in order to help explain the the functionality of my design. And one of the things I'd like to do, if I have time and if you remind me, I bet you don't remind me, I can tell you about micro FP, which was pioneered by someone working at Oxford University in the programming research lab, and it's just a way of specifying circuits using this very special functional programming language FP, which enables it to be transformed, not automatically always, but sometimes automatically, in order to simplify and reduce the complexity of a design. So hopefully there's going to be one or two interesting things. But before I leave the introduction, what I'm intending on doing is to set you a little bit of work on the design of a multiplier in logic. So I want you to think about the problem of giving the logic needed to multiply two numbers and give a result. So we're going to have a look at that problem, and we'll look at it fairly quickly. And I'm thinking of setting a question in that area. Okay, so I think that is the end of my overview. I mean, it seems as though there's a fair amount of material there, but it's you can be the judge of that. And what I'm going to do is to upload the first presentation, which is going to be on mutual exclusion and synchronization. So hopefully this is uploadable and there are no problems. Okay, it's being converted first of all by BBB, and that's worked very quickly. So mutual exclusion, and I just want to, it's not particularly technical, but it's irrelevant. And I just wanted you to have a look at that, because I mean, it's completely not related to what I want to talk about. It's the big white horrible looking object is a grain of rice, and the little metallic looking object lying on its right hand side was apparently the world's smallest complete computer. So it's just to give you the idea of the difference of scale, which I thought was quite interesting. And of course I'm just gonna draw something now, and the world's smallest computer could fit on the dot that I've just drawn, and that is much smaller. That's much smaller than this by now out of date computer, but it's a complete computer, and I think this little computer had built-in wireless, so it could communicate. It could communicate off chip with other similar computers. I don't know why I've mentioned that, but I thought it was just an interesting thought for the day. So the first thing I want to say, and you could disagree with this if you want to, is that mutual exclusion, the idea of mutual exclusion is a very important concept, it's a very important idea. And I want to simply consider the idea of a resource which is needed by an agent to accomplish an action. And again, that is very general. I mean, you might say, well, what do you mean, Kindberg? Do you mean the tool that a gardener needs to dig a flower bed? In other words, a spade. Is that what you mean? Well, it could be. All right. But the surprising thing, and we'll have a look at some examples of what I mean by resources in a moment. Very often, resources aren't shareable. And I guess what I mean by shareability, at least, is physically unshareable and possibly also logically unshareable. So, I mean, even God himself couldn't share such a resource because it's logically unshareable. And I mean, if you're religiously minded, um, it's quite possible that you think God has to obey the laws of logic. He can't create real impossibilities. He can't create environments that are actually internally inconsistent, internally not possible. But maybe you've got views on that. I don't know. So let's think about some examples. And the first example that comes to my mind is the space that your body is actually inhabiting right now. And okay, so I've just put a little flag here. Do I mean physical? Do I mean logic? Or do I mean something else? And I want you to think about, given certain resources that aren't shareable, are we talking about physical impossibility? Are we talking about logical impossibility? The space that your body inhabits and um, the ground on which you're standing is not, at least physically, shareable. I mean, my foot can't suddenly uh, occupy the space that your foot is currently inhabiting. Well, you might say, well, of course it could, but we're talking about a massive injury to perhaps both our feet if we accomplished sharing the same physical space. The printer that's currently printing my essay cannot be shared because it's printing a document for me. And if you think about the construction of printers, um, they have to print documents serially, taking a sequence of lines and printing them out one by one. Printers aren't constructed in such a way that they can print a line of my essay and a line of your essay alternatively at the same time. It can't do it. Other example that comes to mind, I mean, you'll get bored with this. The pair of spectacles I'm wearing, you can't share them to see out of when I'm wearing them. It's not possible. Nor is the chopstick that I'm using to eat my meal with. I mean, think about it. Can we both simultaneously use this resource, use the chopstick to eat at the same time? I mean, we could try, but I think we'd end up in a completely embarrassing situation with food all over the place. You can't share my left eyeball to see out of. You can't share my visual field. I mean, maybe in 10 years' time you will be able to replicate what I am actually seeing out of my eye, but it's not quite the same as sharing my eye or the vision given to me by my particular eye. The car that is just about to collide a lorry, the car is occupying a region of space and a lorry is just about to hit the car. a car and a lorry can't both simultaneously occupy the same region of space without massive damage. And another example, a bit of computer storage, one single bit of storage, can't logically be shared by another process. I mean, a processor can actually write a bit of storage, but the bit of storage can't actually be read at the same time, can't be looked at, can't be examined at the same time. Or two processors cannot write a single bit into one and the same storage cell. And there's a good argument for saying that your stomach can't be shared with, I don't know, a different kind of animal. I mean, perhaps I think that's more physically possible because if you think about it a little bit, it seems as though you could create circumstances where your stomach, perhaps on a pair-need basis, can be shared by another human being for periods of time during the day. I don't know. I mean, that's for you to think about. It sounds a bit disgusting to me, but still. So you might say, but surely resources are shareable. Well, to the extent that resources are shareable, it's quite clear that some are not. So, for example, what I mean by that is that, in a sense, a video screen can be shared by 1 million people or 60,000 people at Wembley Stadium, you know, giving close-ups of particular footballers' moves. Or the sofa that you have in your, let me call it a lounge, can be shared. You know, 3 people can sit on the sofa. That's sharing a resource, furniture resource, isn't it? Or a wide doorway could in fact be shared by 2 people. It might allow 2 people to walk through the doorway in a given frame of time. But maybe 2 elephants couldn't share the same gateway at the same time without there being absolute pandemonium. So I want to claim that many resources of the sorts of things I'm talking about are generally such that they cannot be shared at the same time. And that's really to say, okay, I'll just read on a little bit. I mean, the chair I'm sitting on cannot be shared right now without considerable risk to you and to myself in the attempt to share it. I mean, you know, we're going to get hurt probably, or it's going to be embarrassing, or it's going to be remarked on. That'll be outrageous, I don't know. But the key thing is this: an attempt to share a non-shareable resource easily. So hopefully we're still connected. I did have a temporary power outage. I don't know whether you can hear me. You probably can't. So what I'm going to do is let me see what I'm doing. I'm going to pause the recording. I'm going to try and reconnect. So I'm gonna leave the meeting for a moment. Gordon Bennett. Hi, Mustafa. I had a power outage for a moment, but I'll continue as best I can. So I'm going to start recording again and continue as quickly as I possibly can. So I'm going to upload the same presentation. Hopefully that won't take too much time. I'm not sure what happened. I mean, it restored the screen, but didn't have sound. Okay. So I'll continue as far as okay. So okay, so I'm going to start on the next slide. So why is this discussion important? Why is the content of what I'm saying important? Uh, Simply because typically there is competition for the use of resources, and by that I mean situations like finding a free seat on a bus or an aircraft, or an attempt to now buy face masks, because the manufacture of face masks in this country apparently is being run down, curiously and very oddly. And the use of resources must somehow be organised so that the use of the resource by one agent excludes the use of the resource by another. And the computing science context which I'm interested in is that if I build a system which has as many as 10,000 different threads or programs, I mean maybe 2,000 different programs running on my laptop, they all need resources to survive, to continue to exist. And by that I mean, well, any program needs memory to run. If I'm running a program, perhaps it needs memory to store something. Or maybe if I want to communicate data in a file, then I will need a particular port to send data out, if it's a TCP or an IP port. So these are all resources that come to mind for which there is competition. And maybe it's a huge number of programs and a huge number of resources. I mean, that's. I'm uh, just trying to run my little web camera again, and I think I've got it. So it's okay. So the problem of how these threads or programs, or in fact even nations, I'm talking about countries or groups of people, are to be organised in order that the use of a resource by one country excludes the use of the same resource by another country is the problem of mutual exclusion. And that simply means how I should really say how non-shareable resources aren't allowed to be shared at a given time. So I should really, we're back to this again. Let me try this. So I'm going to try and just put a line here. So how it should be unshareable resources. Just remember it's unshareable. And I'll try, I can't cope with, no, unshareable resources aren't allowed to be shared. How do you do it? What's the mechanism? Um, so, again, I'm reminding you that a failure of mutual exclusion is likely to result that event. Sorry, it's likely that event, the failure of mutual exclusion, will have disastrous consequences. So it could be the start of World War III. It could be a road death. It could be your computer crashing at an incredibly important moment that you don't want it to crash. You know, maybe you're just about to cancel the purchase of 30 bitcoins, and because they're falling so rapidly in price at the moment, and you can't do it because because of some kind of crashing of your system due to the failure of mutual exclusion. And, or it could be a jetliner crash. Many systems failures in computers are simply the result of a breach of mutual exclusion. And remember that. You know, if you see a computer crash, the chances are there's a high probability that there's been a failure of mutual exclusion somewhere. Okay, imagine a mailbox, which I'm assuming is a non-shareable resource, because, you know, it's my mailbox and you're not allowed to use it. It's for the exclusive use of me. And the letter that is going to be posted by the postman into it at the very same time that a letter or message is being removed by myself. There's a very high probability that the letter will be damaged or can no longer be read if those two events take place simultaneously. I mean, letterboxes aren't designed for the simultaneous insertion and removal of a letter. I hope you agree with that. You might think otherwise. Let's just explore this even more. If I start speaking at the same time as you, Mustafa, there's every chance that neither of us will understand what the other has just said. I shouldn't begin to talk until I know that it's safe to talk. In other words, safety of talking involves not using a non-shareable resource. I want to make sure that when I talk to you, you are listening, and I certainly shouldn't talk at the point where you've just started to talk. Otherwise, the communication content will be lost. And however odd it may sound, the air occupying the region between you and myself cannot be shared for talking purposes. So you can think of air as being a non-shareable resource. And one other related situation is when one device can communicate. And I'm not quite sure why I'm talking about this. Is one other situation we should be aware of is when one device can communicate far faster than the other device can understand or hear or listen. I mean, perhaps the message has been delivered in a very short period and contains a massive information, 50 gigabytes of data in less than a second, and in such a way that the other electronic device has no chance of hearing or listening or capturing these signals. I mean, maybe because it can only process 1 byte per second. Maybe the message was delivered at a rate of 1 gigabyte I don't know, per nanosecond, whatever you like. It's a logical, coherent situation. One possible solution to the latter problem, and it doesn't seem to have any bearing on mutual exclusion at the moment, is to enable a device to transmit data at an arbitrary speed, whether or not the other device is actually ready to receive data. And this will involve the use of a buffer. In other words, some shareable memory which allows me, the fast transmitter, to put data into it, and it allows you, the consumer or the receiver of a lot of data, to read the data at a rate of your own choosing. So what we're talking about is the difference between asynchronous and synchronous communication. I mean, I can implement asynchronous communications, and what I mean by that is very simple. Means I can transmit data at any time I want to, regardless of whether or not you're ready to receive it. And that's in contrast to the previous case of synchronous communication, where I'm only going to talk at the point where I know that you are listening and you can receive the data. Okay, so I can use a buffer to implement asynchronous communications, and that's important. And you can think of a buffer as some kind of shock absorber, very much like one you find on a car. You know, when you go over a pothole, like a spring, it's going to absorb possibly large amounts of energy, or data in this case, without losing it before the communication partner is ready to receive the data and to consume it when ready at possibly a very, very slow or a very fast rate. And we've had a look at buffers quite recently in the context of TCP. We looked at sliding windows, where we're going to a TCP transmitter, like a sender or a server can send as many as n bytes, and I'm never going to send more than n bytes. N bytes is my legal restriction on the amount of data I can send. And so a buffer enables us to solve the problem of enabling enable A to transmit data to B, but it wouldn't solve the issue necessarily of the fact that the buffer isn't likely to be shareable. Right. I mean, what I'm really talking about is that if I'm operating with a buffer of data, then it should not be allowed that a sender can access the buffer at the same time as a reader of data or a receiver of data is receiving data from the buffer. It's one or the other, not both per unit time. And you can ask yourself, well, why? Well, supposing the buffer is just a few cells of memory, 8 bits say, and supposing one program writes 8 bits to the cell at the same time another program writes data to the same cell. Okay, so you've got two writing programs, both writing data to the same buffer. What's the outcome? Well, from a physics point of view, the outcome's by no means clear. I mean, it's possible that all the data will be corrupt, or it might be the case that it's a question of first past the post wins. The person that first wrote the data will be the person whose data is actually left in the buffer, or it could be the last of the two. I mean, things don't happen. When I say that A happens at the same time as B, what do I mean? If I'm using a real number to index the time, it's very, very difficult to ever ensure or test for real simultaneity, real sameness of time. So it's likely that one of the other two writers are going to write first and to write last, on a bit by bit comparison. Like maybe process number two was the last to write data into the buffer, so what it wrote is going to stay in the buffer. I mean, it's very unclear what the outcome would be. I mean, we can take steps to make sure at most one of a number of processes do actually uh, achieve um, achieve a successful transmission and achieves unique use of that resource. Razan, I've just seen you. Good morning. Hello. Pleasure to have you here. Sorry about all the emails I've been sending you, but um, we'll talk about things in a moment or two. What I'm talking about today, I mean, it's all self-contained. It's not too technical, but starting at the beginning, we're talking about the impossibility of two agents, two people, two processes of using a non-shareable resource in order to do something, in order to achieve something. And the failure of preventing two people from doing something that they can't actually do is going to result in destruction or hurt or injury or some catastrophe. And a lot of people say that the advent of World War III is going to be due to some kind of technical hitch involving the breach of mutual exclusion. So we're just discussing what mutual exclusion is and why it's important. And I've been a bit long-winded, but it's all being recorded as far as I can see. And I just want you to appreciate the fact that life is full of resources and life is full of people wanting to use those resources, and some of those resources cannot be shared at the same time. I mean, most resources can be serially reused, there's no problem. And in computer science, I'm looking at the problem of ensuring that mutual exclusion is assured, it happens, and the failure of mutual exclusion is prevented as best we can, because it's very serious. I mean, things like aircraft crashes or failure to dock successfully with the orbiting space station is often due to failures of mutual exclusion, things not quite happening as they should have been doing. So I'll continue, but you can stop me at any time, and I welcome any comments or queries or denials, and we'll just continue for a little while anyway. Um, so what are we doing here? I'm doing what is the outcome of two producer programs writing two different 8-bit numbers to the same, I guess the same buffer, sequence of cells, or maybe of 2,000 programs attempting to write to the same 1-bit location? I mean, it will result in a lot of unforeseen consequences and possibly a lot of a lot of damage. Um, so to solve the problem, it's necessary to ensure that when a device writes data to the buffer, any device B is prevented from reading data from it at the same time, or B itself, if it's a writer of data, then it's going to be prevented from writing to the buffer at the same time. And the converse, I mean, I shouldn't allow two different readers to read the same data at the same time. I mean, that raises the issue of, well, maybe you've got some data that needs processing, but why on earth should you want to process the same data twice? I mean, you might want to share data amongst M different readers, but you've got to be very careful about what's happening here. And in addition, whilst we're talking about buffers, we might assume that the system operates or should operate safely. And what I mean by that is that a reader B won't ever attempt to read data from a buffer that's empty. Nobody's put data in it. You shouldn't allow that to happen. You should prevent that from happening. That's dangerous. Or what might be in the buffer is old data. And old data typically is very, because it's not up to date, it's dangerous. Or it might be corrupt, just full of absolute rubbish. And no two or more readers. Okay, so that's saying, and no two or more readers, because there could be 100 readers, all attempting to read data from the buffer. You shouldn't allow that to happen. So in general, resources, as I've said a moment ago, are serially reusable. That's to say, once an agent or a program or a process has finished, or once you have finished using the resource, there's no problem in allowing another agent then to use the resource. And I mean, all I mean by that simply is if I get up from my chair, I'm allowing you, if you want to sit on my chair, to sit on it. No problem. There's no harm being done. There's no reason why you shouldn't. So, little definition here. And the program code that programs contain that accesses or uses a non-shareable resource is called, for some reason, it's called a critical section. It's critical. It's critical mainly because at most one program should be allowed to access this code. And the bit of program that comes before the critical section is called the pre-protocol code. And that follows the critical section is called post-protocol code. I mean, I think it's somebody just inventing terminology for the sake of it. So an example is the need to avoid reading and writing to the file at the same time, or attempting to show two video clips in the same region of your laptop screen. It's not possible. You'll get rubbish if you try to do that, or you allow two applications to put video clips onto the same region of your laptop screen. Or think about it. I mean, you've got, you can actually duplicate this situation very easily. You just run two YouTube videos with sound, and you get this cacophony of sound. You get something like two people singing. Two people speaking at the same time. You can't understand it. It's gibberish. I mean, you might be able to understand it, or maybe a few words, or get the gist of it, but you can't properly understand it. So this is important. I'm going to discuss two operations you find in programming, so I just want you to understand the bare bones of these two operations, wait and signal, and are very easy to understand. But the operation of the two operations, when you use them in conjunction, is a bit more difficult. So I'm using some very simple Python to express the idea of the wait operation. So definition of the wait operation on a buffer, and I'll talk about that in a moment, is this. Whilst the value of the buffer, so buffer is obviously going to be a variable, whilst the value of buffer is 0, don't do anything. Don't do anything. And then when it changes from 0 to 1, you immediately change the value of buffer to 0. So let me just restate that. The definition of the wait operation on a variable called buffer is this. You repeatedly examine the value of buffer, and whilst the value is 0, just don't do anything. You wait. Sing a song. Just wait. No action at all. But when the value of buffer changes from 0 to 1, you immediately change the value to 0. And you might think, this is crazy. What's all this about? Well, let me tell you. You're going to perform a wait operation on this variable before attempting to use a critical section, a bit of code that results in accessing or using a non-shareable resource. How come? How does it work? Well, I'm assuming that another person, maybe Razan, is busy using the resource, and she has set the value of this variable to 0. And the fact that it's at 0 means that Razan or some other process, some other person, is using the resource. But I want to use the resource, so I'm literally waiting until the value of buffer changes from 0 to 1. If it's 1, it means that no process is using this non-shareable resource. And I'm going to grab it by setting buffer to be 0. I'm warning any other processes that are waiting to use the resource that Chris Kinberg is using it. Keep clear. I'm using a resource which, if you were to use it, you'd cause a horrific accident. So what I eventually do, when I've finished using the resource, I perform a signal operation on the variable buffer. And all that does, as you can see, is to add 1 to the old value of buffer. Buffer's currently 0, because I set it to 0 here. I'm going to change it back to 1. And in other words, I'm releasing the resource for public use. You can have it. I've finished with it. So these two operations look very simple. The only thing that I should say is that buffer is a special variable in the sense that the value of buffer can only be either 1 or 0, and certainly not both. Alright, just two values. They're binary. They are okay. What if the buffer is 0? Very good question. So let's supposing I've got two programs, A and B, and A wants to use this resource. I mean, maybe the resource is just this pen here, and I'm going to check the value of pen. It's going to be a variable called pen, and supposing I find that the value of pen is 1. Well, what I do is to test the value and find it's 0. Sorry, find it's 1. So I skip this line and I immediately set the value of pen to 0. And that warns Razan and Mustafa and everybody else in the world that they're not to interfere with my pen. I'm just picking up, I'm going to use it. Don't you dare use it at the same time. Look, there's an attempt by a second party to use it. It's going to be, the pen is going to get broken. So, sorry about that. Amateur dramatics. Right. So, hopefully, so the big question now is, given that the initial value of buffer, okay, so buffer is a special variable, it's 1 or a 0, and it's also called, in respect of being a special variable, binary variable, it's also called a semaphore. Okay, semaphore. And I don't know whether you, sorry, that's not very well typographically arranged, but a semaphore originally was a very important tool used by sailors at sea, and they were flags. And using little, I don't know, coloured flags, they were able to communicate over miles to another sea-going ship. And that's the origin of, I think, the origin of the name semaphore. But you can check that out and just find it out on Google or something. So have a look at this code. I've got two little programs. I've got program 1 called a writer, and program 2 is a reader of data. And in the background, I mean, I've got something like, oh, my drawing is appalling. I've got a buffer here, and I've got a reader at this end, and I've got a writer that end and a reader this end. And I've got some data. Let me just abbreviate. That's appalling. I've got some data in the buffer, and the writer wants to write data to this sequence of memory, or chunk of memory, and the reader wants to read data from it. And I want you to think about this, what happens if the initial value of the semaphore is 1. So let's start on this side. Well, okay, I'm not going to do that because I don't want the reader to attempt to read data from an empty buffer. I mean, I can fiddle around with this to make sure it's not going to do that. But let's assume that the writer does a little bit of work. It says hello to Razan and hello to Mustafa, and then it's going to wait on the buffer, and it's going to find that the value of buffer is 1. So the thing it does straight away is to set the value of buffer to 0, which informally means Chris Kinberg is using the buffer. Stay away, keep off it. And program 2 might come along and say, okay, I want to read some data. But in these circumstances, it's going to find that the value of buffer is 0, and it's got to literally and figurative wait. It mustn't do anything, so it can't read data from buffer yet. And meanwhile, back at home, the writer actually succeeds in writing data to buffer. It's telling um, Razan something important. I finish writing the message, and the last thing that the writer program does is to signal a buffer. In other words, buffer now becomes 1, and the reader has been waiting for buffer to change from 0 to 1. It's now 1. So it's going to, the first thing it's going to do is to set the value of buffer to 0 to prevent me writing more data to the buffer. It will then read data from the buffer and then give me permission to write data to the buffer by signaling the buffer. And remember, a signal operation on a semaphore simply results in increasing the value of the semaphore by 1. And the question is, does this guarantee mutual exclusion of the buffer when the programs are executed in parallel or concurrently? Because we're obviously talking about a world in which things happen concurrently or in parallel. And if that's the case, then it's a partial solution to the so-called producer-consumer problem. Okay, so in the coursework, one of the questions is going to be what's meant by the general producer-consumer problem. And I'll talk a little bit about that in a moment. I mean, it's very easy question, right? But it's not a complete solution because we haven't addressed the problem of preventing the reader from reading from an empty buffer, or we haven't prevented a producer from writing to a buffer that's already full. I mean, Razan, what is the point of writing more on an essay if you finish the essay? The essay's full. It's done. What's the don't be tempted to write any more, as it were. Right. So we'll return to this later. In fact, in a few minutes. Right. So what I can do, so as a sort of an immediate hint, is that I could have another semaphore called available. And after writing data to the buffer, the writer signals available. So it increases the value of available, assuming it's 0 to 1. And when the reader consumes an item, when it wants to consume an item, it will perform a wait operation of available first, and in this case it will find available to have the value of 1, so it's going to change 1 to 0, and the reader needs to wait on the... So in other words, the reader will need to wait on a second semaphore called available. I'll set all this out in a moment. Right. So I'm just going to pause for about 10 seconds whilst I... okay. So I'm just going to talk a bit about synchronization. Then I'll give you a little example of two programs which satisfy mutual exclusion in every possible way. So turning our attention to synchronization, the issue of synchronization is also very important. I shouldn't communicate with Razan unless Razan is ready for me to communicate. And how do we manage that? How do we create a mechanism to force that situation? A simple non-technical solution is to, as I've already mentioned, is to implement an alternative scheme, asynchronous communication using a buffer. So I don't know whether you were present, Razan, when I started talking about asynchronous communication in these slides, but I have done, so don't be too worried by this. I can use a buffer in such a way that I can fill it with data I want Razan to hear. And I really don't care at the moment whether Razan's asleep or whether she's listening. When she's awake, when she's ready, she can look at the buffer and read my message to her. But what if you can't use a buffer to implement asynchronous communication? What do you do? I mean, how do I synchronize? How do I communicate with you if we're two different independent systems with our own clocks? We're operating at different rates. Well, one general method is to allow the communication partners to perform a handshake. And I'm sure, you know, if you've looked at some of the work that the rest of the course has been doing this year, you'll find quite a bit of material on handshakes. And what a handshake simply means is that if I want to talk to Razan or Mustafa, what I do is to raise my hand as though I was about to perform a handshake, and I'm going to keep my arm in that position, and I'm going to keep it there until Razan actually sees my hand raised. And when she does see it, and this is the essence of synchronization, when she does see it, she's going to let me know that she's seen my offer to communicate by raising her hand. She outstretches her arm as though she was going to shake my hand. And when she does that, eventually, when I see that happening, because it might take a bit of time, when I see that happening, I will lower my arm, which tells Razan that I've actually seen her raise her hand, and as a result of Razan seeing me having seen her preparedness to talk, she will lower her arm. And at that point in time, both Razan and Chris Kimberg are going to be prepared to talk to one another. This is achieving synchronization by means of a handshake. And you might think, well, how does all this fit in? Well, you're going to have to think a little bit about that, okay? And I'm just going to do a little bit more, and this you might find this a bit funny or tricky, or might be a better way of doing this. But I want to try and solve the mutual exclusion problem purely by software alone. And I'm imagining two processes, P1 and P2, which are just, they're operating in an infinite loop. They're repeatedly processing some data and then wanting to put it in a buffer to send it to somebody else. And each of P1 and P2 contains a critical section. And as such, the two critical sections, CS1 and CS2, must not be allowed to overlap in time. And let's supposing we build an igloo, and the idea of an igloo, to illustrate what's going on, is due to someone called Professor Ben Ari, which I thought it was quite amusing. Containing a whiteboard. So we build an igloo, a single igloo, containing a whiteboard and some black chalk. And the construction of the igloo is designed to ensure that only one process can crawl through the entrance at a time. So you can't get two Inuits enter the igloo at the same time. It's not possible. So written on the whiteboard is the identity of the process whose turn it is to go next. So we're trying to implement a mechanism for ensuring mutual exclusion, and this is what we're doing. So let me give you the diagram. I hope you can see that. So here's the diagram. Here's the whiteboard, and it's got using the black chalk. The turn of the next process to do its critical section is process number 1. Here, this lady here, it's her turn. She's been given the term on the basis of a 1 having been written on the whiteboard. Not both P1 and P2 can get inside the igloo. I think if P2's inside, it's impossible for P1 to actually enter, and certainly both can't enter. As you can see, it's quite a narrow entry point. And the code looks like this. So have a look at this. Process 1 means forever. It means repeatedly do all this again and again for all eternity. So this is P1, and P1 says, whilst it's process 2's turn, while the number written on the whiteboard is 2, don't do anything. It's not your turn. P1, it's not your turn. Wait. But when T becomes 1, I'm going to do my critical section. And after I've done my critical section, I'm going to crawl into the igloo, use the black chalk, and write T2's turn. T is 2. And meanwhile, so we've got to think concurrently here in parallel. Exactly the same. So I'm repeatedly executing these instructions, this computer code. While so this is P2. Whilst it's not my turn, don't do anything. But when it is my turn, so when T does become 2, I'm going to immediately execute my critical section. When I've finished, I'm going to give the turn back to P1. So initially, I think what's the initial value of T? I don't know. Okay, it's 1. So I'm giving the first turn to process 1. I'm setting T to be 1. I'm writing T on the whiteboard. Think about this. It solves the problem of mutual exclusion because either P1 or P2 does its critical section if and only if it's that process's turn. And T it's not both 1 and 0, so deadlock's impossible. And because either it's T's turn, either it's T1's turn or it's T2's turn. It's not possible. There's no third possibility. It's one or the other. So I want you to think about this and simply convince yourselves that mutual exclusion will always hold. Okay, one or the other. Think about this. I mean, it's a bit like the operation of semaphores. You're having to wait whilst it's not your turn. And when it is your turn, you make sure that the fact that it's your turn is recorded to warn other processes off. Make sure they don't execute their critical section either. So, but, or therefore, exactly one process progresses, it does its job. It's not possible for both P1 and P2 to be stuck in their respective while loops. If each process takes a limited amount of time, the process whose turn it is to do critical section will eventually do so, and it will then allow the other process to enter its critical section. So I'm claiming that is the case, and it's a bit up to you to convince yourself that's true. I mean, you probably could prove it, but I'm not asking you to do that. Excuse me. I'm not asking you to do that. Right? But the two processes are what's called loosely connected. And in other words, the right to enter a critical section is explicitly passed from one process to another. In other words, if I'm P1 and I've just done my critical section, it's up to me to crawl into the IGU and to give the other process its turn by writing it on the whiteboard. So I want you to think about this, because this is the major operational fault in this scheme of implementing mutual exclusion. Supposing Chris Kinberg needs to do its critical section 1,000,000 times in a second. I've got to do something very important millions of times per second. But P2 only needs to do its critical section once a day. And maybe it takes an hour to do, or maybe it takes 6 hours to do. I don't know. But think about it. P1 is going to execute its critical section. In other words, use the non-shareable resource for the first time, and then P1 is actually going to pass the right for P2 to do its critical section to P2 by writing 2 on the whiteboard. Well, what happens? Well, P2 is only going to attempt to use its critical section once a day. And in other words, P1 is going to have to wait a very, 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 very long time before P2 actually gives the right to P1 of executing its critical section. And it might have to wait all day, which is crazy because P1 needs to do its critical section. It needs to burn 10 cubic centimeters of fuel in its thruster rocket 1,000,000 times in a second. I don't know, something along those lines. So the conclusion, if you think about it, is, unfortunately, P1 is going to be forced to work at the rate at which P2 is operating, and that's not a particularly good solution, is it? And but if that wasn't bad enough, another problem is this: P1 waits for P2 to execute its critical section and change the number from 2 to 1. At the moment, if P2's executing its critical section, P2, uh, P1 will have written 2 on the whiteboard. So P2 now wants to execute its critical section, and it wants to change the number from 2 to 1. And it will do that if everything goes normally. But supposing P2 is eaten by a polar bear, then let's just go back a slide, or 2 slides. Supposing P2 is executing its critical section, the implication is that T is 2. That's why P2 was allowed to execute its critical section. The next thing would have been to give the turn back to 1. P2 will crawl into the igloo and write 1 on the whiteboard. But supposing P2 is eaten by a polar bear, it'll never ever get to execute this statement here, putting T back to 1. And meanwhile, back at home, P1 is patiently and ridiculously and in vain waiting for T to be changed to 1. It'll never happen. So in other words, for all eternity, P1 will spend its time waiting for an event that will never happen. And it's very sad. Right. So can we deal with this problem? Well, there is another attempted solution, and I'm not going to take you through it. You build 2 igloos, and there's quite a bit of toing and froing between the 2 Inuit people. We're going into one another's igloos and doing this and that. I'm not going to explain that to you here. But there's another attempted solution, and you just have a look at this. See if you can make sense of it. And this is the code. Right, I'm using 2 separate whiteboards, and it might prevent the problem of what happens if P2 is eaten by a polar bear. This process will still continue. Have a look at that anyway. But the problem with this is that mutual exclusion isn't guaranteed in every case. And I'm showing you a case where P1 checks it's right to go and it finds it's 1. That's okay. But P1 checks it's right to go. It's going to check CS something on the whiteboard for CS1, and it finds that's okay. And P2 is going to check CS1 and find that it's 1. So P1 and P2 are both going to change CS1 and CS2 to 0. And that has the consequence that P1 and P2 both execute their critical sections and World War III starts. Simple as that. Um, so, uh, okay, that's all I'm going to say. And there might be, I think there are another two software attempts to deal with this. I'm not going to go into them. I mean, I just want to tell you that the use of semaphores is adequate. It doesn't suffer from any of these problems, and we shouldn't be too concerned that in software alone, it's very difficult to produce a convincing solution to the problem of mutual exclusion. And as I started off by saying, Dijkstra succeeded and provided. I think it. No, 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 no. I think it was actually. I think it was someone called Lamport, a Dutch. Again, he was a Dutchman. Lamport um, uh, discovered rather than invented a solution to the problem of mutual exclusion in software, but it's quite complex, and I don't want. It's not necessary for us to understand that. Okay, so any questions arising from that? Can you cope with that? So let me just summarise what I've done. I've defined a semaphore, and I've shown how the use of semaphores can implement a workable solution to ensuring mutual exclusion. And logically, I can prevent uh, all sorts of horrific damage from happening armed with this mechanism. And remember, the world is dangerous. There's competition for scarce resources, including food. If you don't gain that resource, you're going to die. It's as simple as that. So think about the generality of what I'm saying, and think about how I've narrowed the problem down to one in computer science. And I'm using this abstraction called a critical section to represent the accessing or use of a non-shareable resource. And think about resources too, which are shareable, which aren't. You form your own opinion about that. Okay, so I'm going to take about 20 seconds off. But if you want to ask me any questions, if you're happy to reflect on all this, I'm happy. Um, I'm happy as well, But I will be setting a couple of questions on this week's assessment on this part of the session. So if there's something you really don't understand, you can ask me now, or perhaps better still, just send me an email, and I'll give you a written answer or written support. So I'm going to now change to my second um, presentation on, if I can find it, on Boolean algebra. So it's being processed quite quickly, and it should appear in a few seconds. Okay. Just out of interest, Razan and Mustafa, I know Mustafa, you're in London, aren't you? Razan, are you in London at the moment, or? Okay, so can you send the presentation? The presentation will be, Razan, the presentation will be put on to Veros in the next, I guess the next hour and a half. I mean, I will always give you everything, and I'll also put the a reference to the recording. You should find it, if the recording's successful, at the moment I've got 63 minutes of recording. You'll find it in the BBB area, but I'll put a clone of that up on Veros, no problems. Okay, so I want to change focus and talk about Boolean algebra, and I'm sure most of you will. So Razan, you didn't tell me whether you were in London. Are you in London at the moment? So it's just out of interest, because one of my students I thought was in London, and he really. Okay, so you're not in London. Where are you? Can you tell me? One of my students was supposed to be in London, but he actually. Then I thought maybe he's in Hong Kong, but then he really surprised me by telling me that he was actually in Shanghai, and he sent me a couple of images of what life was like in Shanghai, and it's absolutely Vienna. Goodness, I'm envious. Good for you. Okay, so thanks for telling me. So let me return to the task of talking about Boolean algebra, and intended learning outcomes for this part of the session is I want you to understand what a Boolean expression is and how you construct them, what the rules are for constructing them. And secondly, what truth tables are and how they represent Boolean expressions in all important aspects. And I want to define fairly rigorously the logical operators and or not on their own or grouped together. Fourthly, I want to show you how to use Nand and NOR and exclusive operators. And then I want to hint at how you can simplify Boolean expressions. Then I want to talk about De Morgan's laws in order to create Boolean expressions which primarily use Nand and NOR expressions. So that might seem a fair amount to do, but sort of fond of reminding people that 2-year-old children have a very good understanding of logic, and it shouldn't present any problem. So the key idea is that, so wait for it, this is important. The key idea is that logical expressions, so things you write down, are actually truth functions of their constituent parts. And what I mean by that is that the truth or falsity of a complete and possibly complex expression is determined uniquely by the truth or falsity of its component parts. George Boole developed the algebra named after him in the 1870s, so it's a long, long time ago. And the algebra is closely related to this construction of logic gates, the development of which came a very considerable while afterwards. I mean, not until, I don't know, until the 1940s, a long time afterwards. So, examples, very simple examples. Consider the sentence, because it is a sentence, 1 is less than 7. I mean, it's a mathematical sentence. 1 is less than 7. And it's actually true. And it's an atomic sentence because it doesn't contain parts, it doesn't contain sentences as a part of it. CK is aged 17 years old and he has a passport. It's a sentence, but it consists of two parts, two subparts, two sentences. I mean, CK is aged 17 years old and CK has a passport. Consider another mathematical expression. Either x is equal to or less than 10 or x is greater than 10. It's actually a mathematical truth, isn't it? And simple sentence, CK teaches at IFG and Oxford. Well, I suppose you could break it down into two sentences if we wanted to, but I don't see that there's any particular need for doing that. CK teaches at IFG and Mustafa. That's not hard at all to write a truth table, as I'll show you in a moment. CK teaches at IFG and CK teaches at Oxford. Okay, maybe it's built up out of two separate sentences, each sentence being either true or false, but not both. So the key thing to notice here is that the second, third and fourth sentences are relatively complex and are built out of two sentences. For example, the second sentence results from ANDing two sentences together. And when speaking of a sentence's or an expression's truth, we can think of the truth value, i.e. whether it's true or false, being either, represent that by being 1 or 0. We can think of the truth value of a sentence as being either 1 or 0. So that if A stands for or represents a sentence, A equals 1 simply means A is true. I mean, okay, so Boolean algebra can help to determine the truth value of any logical sentence. So for example, supposing we've got two sentences, A and B. A is the button is pressed. I should really have written the button is pressed in inverted commas, but I'm not, just for simplicity. And B is the sentence, the Bombay door opens. Then we can represent the relationship of A and B with the result of ANDing A and B as follows. Let's do that. So here is one of an example of a truth table mentioned by Mustafa just now, and I've got sentences A and B, and I can regard those as being inputs into the sorry, I forgot what I'm doing. Of the AND function. I should have been able to swap that. So if the sentence A is false and the sentence B is false, then the output, the resulting sentence, is false. So I can't even can't even remember what the sentence was. I think it's Bombay door button. Okay, pressing the button. So if it's not the case that the button's been pressed and the Bombay door is not open, then the button's been pressed and the Bombay door is open. It's false, obviously. On the other hand, if sentence A is true, namely the button has been pressed, and the sentence the Bombay door is open, then the sentence, the output, the result of constructing a sentence, a new sentence from A and B, is true. And in general terms, if you have n inputs, in other words, you've got a sentence built from n different sentences, there are going to be 2 raised to the power of n different input combinations. And the output column will give the truth values for the given pair of truth values in our case. But maybe you've got A, B, C, D and E. So you've got 2 raised to the power of 4, 16 different combinations of values of 4 variables. And you've got to calculate the output, the truth or falsity of the complex sentence. So the table shows that A and B is true if and only if, so notice this expression, if and only if is true, A is true and B is true. So A and B is true only when 2 sentences are true, and if they're true. Right? So this sentence I've got here, so look at this, I've got A dot plus /C dot A plus D / etc. 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 What I've got is 6 different sentences. I've got A, B, C, D, E and T. And just to explain this in advance of what's about to come, plus means in logic or, full stop or period means and / means not, just not C. So A and B, or not C and A, or D and not E, or not A and T. That's 6 sentences. Okay, so is it true or false? Well, it all depends on the truth or falsity of each component sentence. So A can be true or false, B can be true and false, and so on. So you've got 2 raised to the power of 6 different input possibilities of true and false, and you've got to work that out. This sentence is a function, a truth function of all the component sentences like A and B. Well, that's itself is a truth function of 2 sentences. So this sentence, A and B, or not C and A, that's a truth function of the sentences A, B, C and A. Anyway, can use relational operators. So when you're learning Python or Java, you are given the relation operators such as less than or equal to, is the same as, is not the same as, is greater than or equal to, and strictly greater than. Right. So Razan, you're asking, how do you know the output and the input in a sentence's value? Okay, it's a sensible question to ask. Let me have a look at this. You want to find out whether this particular sentence is true or false. The only way you can determine the truth or falsity of this sentence is by evaluating whether or not A is true or false, and determine whether B is true or false. So maybe you know that A is true, you know that B is true, you know that C is false, and so on and so on and so on. You can actually work out what's called the truth value of the entire sentence based on your knowledge of the truth values of individual Okay, so we'll have a look at some examples. So we looked at that. Um, so we're looking at and. So okay, so what we've actually achieved is that we know how to establish the truth or falsity of a sentence that has the form A and B. Well, the truth of A and B simply depends on the actual truth value of A and B. So if A is false and B is false, A and B is certainly going to be false. There's no question about it. If both are true, then the sentence A and B is going to be true. So let's have a quick look. We'll try and move quite quickly through this. Um, so an OR expression is true when at least one of its component statements is true and false otherwise. So if A is the sentence or statement has a passport and B is the statement has a driving license, then the new sentence formed by using OR, represented by plus A or B, is true if and only if at least one of A and B is true or both are true. A or B. A is true, A or B is true if A is true or B is true or both A and B is true. So A and B, the sentence intuitively means that the person has a valid form of ID, and as I've said already, plus means or, and sometimes you get a lowercase v meaning or to represent the logical operator. And the truth table can be summarised by this. So A and B, you've got two inputs, so there are four different possible inputs, truth inputs, A 0, 0, 1, 0, 0, 1 and 1, 1. And the resulting sentence has these truth values. If A and B are both false, then the sentence A or B is false. If A and B is true and false respectively, well, A is true, so it makes A or B true, and so on and so on. And if both A and B are true, then A or B is certainly going to be true. So not operation, dead easy. Supposing we wish to find the truth value of a sentence of the form A and not B. For example, it's 1 p.m. and we're not close to Wigmore Street. So you can represent it's 1 p.m. by A and we're close to Wigmore Street by B. And the truth table for A and not B is given by this. So we've got four possibilities of truth values for A and B, 0, 0 all the way through 1 and 1. So let's look at the value of A and not B. Well, we know that A and not B is true if and only if both A and not B are true. So in this case, A is false. So straight away we can actually say that A and not B is false. But let's have a look. B is false, so not B is 1. So A and not B, even though not B is true, we've still got A and not B being false. So supposing A is true and B is false, then not B is going to be true. Alright? And A and not B, because I've got A is true and not B is true, means that the whole sentence A and not B is true. Here, it's true. It's true. So the truth table for not A is dead easy. You just invert the truth value. So if A is true, then not A is false, and if A is false, then not B is true. It's about as easy as it comes. So combining expressions, supposing that whether data has been read from a barcode reader depends on whether the barcode reader is on and the data has been scanned, or the data has been manually entered. So I can represent the three sentences by A, B and C. Like A represents the barcode reader is on, and B is representing data has been scanned, and C is representing the data has been manually entered. I could represent this English language sentence very concisely by writing A and B or C. So I hope you agree with that. And I can move to a Nand operation, which I mentioned at the outset. And it simply means Nand stands for not and. So we know that an AND operation results in true if all inputs it's composed of are true. But a NAND operation is only true if not all of its inputs are true. So have a look at the truth table for that. And I can represent NAND by / A and B. And what this means is not A and B. So NAND means neither A or B. Sorry, neither A nor B. And that's the same as not A and B. So for example, if A and B are both true, then not and is false. Neither is false. Neither A or B is true. If in fact A and B are both true, then neither A nor B is false. And the only time, sorry, that's a mistake. If A and B are both false, then neither A and B is certainly going to be true. And if A is false and B is true, then it's not the case that A and B is certainly true. And if A is true and B is false, then it's not the case that A and B are true is also true. Not both are true. It's not the case that both A and B are true. So that's a NAND operation. A NOR operation is this. It's neither nor. Neither A nor B. So only true if both A and B are false. Neither A nor B is true only if A and B are both false. If either A and B is true, including both A and B are being true, then neither A nor B are all false. I hope that's okay. I hope that you understand that. Should do. So this is an important operation. So this is a very important operation. It's called exclusive OR, and the exclusive OR operations returns true only if one exactly of its inputs is true, and it's false in every other circumstance, and its truth table is this. And I've even got a special symbol. It looks something like that. Exclusive OR. So it's only true when exactly one of its two inputs is true. Well, here's the case where one of its inputs is true, and exclusive OR of A and B is true. Here's another case of exactly one of its inputs being true, and the exclusive OR of A and B again is true. It's true. But surprisingly, exclusive OR, if both inputs are true, then the exclusive OR is false because both of them, not exactly one of them is true. Both are true. That's false. So in that case, exclusive OR is false. And just a bit more, it's a little bit harder. Simplification. Often it's important to simplify logic expressions as far as possible. And this is relevant to the building of logic circuits because the simpler the logic expression, the fewer the number of logic gates, the hardware gates that have to be built. The fewer are the number of logic gates needed for a system to be built. And it may be important for clarity to be able to simplify the logic description of a circuit. I mean, if I wanted to explain it to Mustafa, the simpler I can get the logic expression to do, the easier it's going to be for Mustafa to understand it. But importantly, if I can simplify a logic expression by removing, say, 30 different logic operators, that probably will translate into a far more inexpensive circuit to produce if I'm about to manufacture 100,000 of these circuits. In other words, each system, each circuit will contain fewer logic gates. And I don't know how well you can see this, but I think the document I'm going to give you is quite clear. I want you to have an awareness of these rules. So A ANDed with anything that has a value of 1 is equivalent to A, and A ORed with anything with the value false is going to have the truth value of A. It's equivalent to A. A ANDed with 0 is 0. A ORed with something that's true is always going to be true, because you're saying either this or that's true, and yes, the second element, the second component certainly is true, so the result is true. Independence law, A ANDed with A is equivalent to A. That's intuitively very reasonable. A ORed with A is going to have the same value. I mean, if you wanted to, you could take this, give me a truth table. Give me the truth table for A ORed with A. You will get the same truth table as you get for just A on its own. So there's an inverse law. Say A ANDed with not A is 0. It's false. So this is, I guess, called a logical truth. It's not possible for both A and not A to be true. And here's another logical truth. The result of ORing A with not OR is always true. A or not A. It's like me saying, Razan is 5'8", or she's not. That's true. Commutative law, A ANDed with B is the same as B ANDed with A, and A ORed with B is the same as, has the same truth value, if you like, as B ORed with A. And then you've got three laws, another three laws here. So associative law, A ANDed with B, then ANDed with C is the same as A ANDed with the result of ANDing B with C. And the same for disjunction, or. A ORed with B, then ORed with C is the same as A ORed with the result of ORing B and C. Nothing terribly intuitively unsatisfactory, it's quite obvious. So A ORed with B and C is equivalent to the result of ORing A and B and then ANDing it with the result of A being ORed with C. So if you don't believe that, give me a truth table. And the same with and A ANDed with B or C is the same as A ANDed with B or A ANDed with C. Okay, absorption law, A ANDed with A or B is exactly the same as A. The truth value of this expression is obviously going to depend on the truth of A. Like if A is false, then false AND with A or B is certainly going to be false. And if A is 1, then this A is going to be 1, and true ORed with any other sentence is going to be 1. So you've got a true AND with a true, which gives you a true. And then the important law is De Morgan's. So just highlight this, and I want you to think about this. So it's a way of converting an OR expression into an AND expression. In fact, the negation of an AND expression. So what I can do, I can say that not A ORed with not B is exactly the same of negating A and B. So I'm getting rid of the plus here. Sorry, or the other way around. I'm replacing an and sign with an expression involving just a plus sign. This is important. And I can get rid of a plus sign here by replacing it with an and operator here. So neither A or B is equivalent to not A and not B. So again, if you don't understand these at first glance, just write the truth tables out. Okay. So here, I'm afraid it's not clear here, but I've got overbar. So that's the same as writing two forward slashes. Not A is equivalent to A. If you say it's not the case that Chris Kinberg is a thief, it means that Chris Kinberg is a thief. Double complement law. So, and I should have really said that these overbars are simply forward slashes to represent not. So A and not A is always false. No matter whether A is true or false, you can't have, it's not possible. Even God couldn't create a universe in which A and not A are both true. So you can think about all this. And here I've given a list of explanations of some of the like A and not A is it. Why is it? Well, the variable ANDed with its inverse equals here. Just giving you a little verbal explanation. And I'm talking about simplification here. I mean, obviously, we've seen how A ORed with A and B, it has the same truth value of A on its own. So another way of looking at this is I can simplify this expression just by deleting it and replacing it with A. So this sentence means that A or A ANDed with B is A and can be proved by looking at the truth table. Okay, so and so on and so on and so on. And it's worth having a look at this case because I'm attempting to simplify this rather nasty looking expression, and what I get is a beautiful simplification. I could simplify this expression all the way down to b using the rules I've given you. Okay, so hopefully it's not too much to contend with, and I'm sort of running out of time now, but I want to make best possible use of it. I'm just showing you the symbols for logic gates. So the symbol for a hardware AND gate, if I input two signals and AND them, I'm going to get A and B. And I've got two signals here and I NAND them, I'm going to get, and it's written like this. This is a NAND gate, but I'm writing a little circle here to represent NOT. So that's NOT A and B. The NOR gate is equivalent to the NOT of A or B. The exclusive OR is written with this sign here, is represented by this sign here. So an exclusive OR gate is represented by this symbol here. A NOT can be represented by, forget that. The negation of A can be represented by a NOT gate. And I don't want to, I'm not interested in using an exclusive NOR, because I haven't even spoken about exclusive NORs yet. So you can ignore that. Just ignore that for the time being. So summarising De Morgan's law, this is another way of simplifying or otherwising change of the structure of a Boolean expression. And what I mean by that is that you can simply change ands to ors and ors to ands if you want to, and then you invert the whole resulting expression. And the target, if you're a hardware engineer, your target might be just to have nands or NOR gates to design and build computing systems. So the basic principles of the use of De Morgan's laws are the two rules, and I want you to know these inside out. Right? And what I'm talking about, just to give a little fancy description of it, that this expression here, not A and B, is substitutable for the expression not A or not B. And the two expressions are substitutable salva veritate, and simply means that you don't change the truth of the expressions by making a substitution. And the second rule, it's just two rules. Not A or B is exactly the same as not A and not B. And I can summarise those two rules by writing that. So I want you to know this. I want you to intuitively to understand the meaning of these two rules. And I can I could justify De Morgan's laws by using Venn diagrams. So if you have a look at the two sets A and B, then the area outside A or B is X. Let's call it X. So the blue area is X, and X is actually could be written as not. My writing using this keyboard is awful. Not A. This is stupid. I'm just wasting my time, but hopefully it's just giving you. So blue area can be represented by this expression: x is not neither A nor B. That's this blue area here. But it also, the blue area is represented by not A and B. Alright, so if you were to write that expression, you could actually equally describe the blue area as writing everything outside the circle A and, ORed with everything outside the circle B. And you get the blue area. So you get not A or not B. X is equivalent to not A or not B. And that is exactly the same as this area here. And that this is sort of like a justification of one of the laws of De Morgan. And what I'd like you to do over the next week is just to consider this here. Just consider it. Just follow it, what I'm doing. So I'm actually simplifying the not of A ORed with not A, and I think that's an ANDed with not B. So what I can do is to replace this expression, not A and not B, by this expression here, and so on and so on and so on. And eventually I end up with the expression not A or B. So I've reduced this rather nasty looking expression to a much simpler expression A or B. Just to get some benefit from this session, just try and work through what I've been doing here. Just try and follow the transformation. And then what I'd like you to do, have a go at, this might form part of the basis of my assessment. Can you simplify the following expressions, or some of them? I haven't decided yet. And one question I gave students to do on their main assessed coursework not so long ago was, can you simplify this expression here? And it looks just a bit tedious. A, not A, or not B, or not A or B. And I think you should have been able to get this not A or not B as a result of simplifying it. And I might even ask you to do this, giving you a head start by giving you a solution here. But you have to understand the first step. But leave it to me, right? Still got a tiny bit of work to do. Or should I do this? In fact, I might leave this part of the present, because I make it nearly 20 minutes past 1. I think I'll leave this subtopic until next time, and then I might give you a little presentation. I think I've spoken enough to you about enough things so that I can actually give you a fair assessment. And you can, when you look at the assessment, hopefully tomorrow night, you can ask me questions if you want to. Okay. And I sort of note that Ahmed's not here, so I don't know whether he's working or whether he's just thoroughly bored with all this. Hopefully not, because he wants to do, I think, computing or engineering. So I'm going to talk about half adders next week, but you'll get this presentation, um, as I said, in about an hour and a half's time on Pharos, and it's quite interesting because it shows. Well, okay, before I leave you, um, let me ask you all both a question. Um, how would you add two bits together? And I want you to add one and one, two digital bits together. What's the result of doing that? Adding one and one together. You add one and one together. Well, actually, I've got this the answer here already. It actually gives you 1, 0. If you're adding binary 1 to binary 1, which in and as a binary sequence, you're adding uh, 1, which is actually 2 raised to the power of 0 to 1, 2 raised to the power of 0. What does it give you? It actually gives you 2 raised to the power of 1, 0. As a binary sequence, it gives you the sequence 1, 0. So what I want to do next week is simply to build a little bit of circuitry from logic alone that enables you to add two numbers together. So, okay, well, you might be mystified by this. I don't know. I've no idea. But we'll continue for about 20 minutes to half an hour next week. So, Mustafa and Razan, I hope you'll be in attendance next week, and I hope you get in touch with me if you want to ask me about the details of coursework or whatever. So I'll finish there. So, okay, just to summarise, I mean, I'll put all the presentations up on Pharos. I guess in the next hour and a half, I'll give you the assessed coursework by tomorrow night, and the BBB video clip will be probably have been manufactured by about 4 or 5 o'clock today, and I'll certainly put my own private recording up on Pharos as well. So both of you take care, and as I said, I get a bit tired of telling you, but if you need to contact me, if you want to contact me, if you want to make a comment, you want to ask a question, just get in touch with me on my email. So can I just give you my email again? So I never actually showed you. I'll do that. My email is simply Kindberg or Kindberg, or in Swedish, Sheenbury. So doesn't like me doing this at all.
Hello, sir. Can you hear me?
I'm trying to write it on the screen here, but I can't do it. Let me see if I can write it. So my email address is Kindberg. If you want to talk to me, you can contact me by email by kindberg@kindberg.org. Okay, Kindberg.
Can you hear me? Because I
Yeah,
got a problem with the mic.
yeah. Or I mean, if you want to, you can contact me on chris.kinberg at on the IFG email. I mean, it's the
I
one.
just got one question
Yep.
considering the coursework.
Yeah. Go
There
ahead.
is there is four coursework. There are four assessments, right?
Well, there's going to
So
be in total there are going to be 5. There's the one you should have done before term ended. I in the week, I think I set it on the last meeting that we had before the exam week, and I said hand the work in 2 weeks' time. And I've I've submitted. Sorry, let me say that again. I've actually published 2 short courseworks since teaching started on July the 5th. this is what I'll do is to give you a third tomorrow, and I'll probably give you a
Okay, so you basically published two. You built two of
well
the
well
assessment.
well they're all up on Pharos so
Yes,
far.
I'm quite aware of two. One of them published in the
Well,
revealed at
well,
Synchronous.
okay. The last session that we had before the exam week, I asked you to do 2 of 5 questions, and I gave you that. I handed out that, put the document up on Pharos. I just want you, and it's to do with, I think it was to do with, I mean, the question involved slow start in TCP. So, you know, you need to have a look at the work that I've done on TCP slow start to finish that. And I mean, it might be a bit, quite a bit for you to do, but I'm sure you can, with a bit of concentration, do it all. And if you need any support, just get in touch with me. Okay.
Okay, yes.
I mean, if you want a live session, I'm quite happy to take you through the work and some of the basic stuff. So just leave it at that. I'm sure you'll be able to cope with that easily. Okay, but I'm here if you want me. All right.
Okay, it's fine.
Okay. Bye bye. So I'll shut the meeting down. So Mustafa, take care, and I'll see you in a week's time, hopefully, if you're still here. All right.